Hello everyone! On behalf of the EnvirVis team, I would like to welcome all of you to this year's workshop on visualization in environmental sciences. My name is Katrin Feige and I am one of the co-chairs of this workshop besides Shomo Dutta, Carsten Rink and Dirk Zeckzer. I have the honor to chair this year's first workshop session, and I must admit that I'm very excited to do so because of the interesting format. So due to the conference going virtual, it's possible for a lot more people to get to know the pieces of research that are presented here. But what's this workshop about and what's its mission? So the background is that research in environmental sciences is becoming more and more important. There are a lot of topics that impact the entire population of the globe, such as climate change, water scarcity, or environmental pollution, to name just a few. And with the increasing importance of research into this direction, also the size and complexity of the necessary underlying data sets to conduct this research grow. So there are multiple data sources that need to be integrated to gain new knowledge, such as data from simulations of different kinds and data from measurements, be it in situ or even remotely sensed. And all of these data sets have their individual data types, temporal and spatial resolutions, data qualities, and also uncertainties. As such, visualization is, on the one hand, a vital component in the process of understanding environmental phenomena described by the data in the research context, but it can, on the other hand side, also help practitioners to make informed decisions or to help engage the general public in environmental topics. So with this background in mind, the EnvirVis workshop has the mission to raise awareness to the importance of visualization in the geosciences, and at the same time, it should be a forum for interdisciplinary discussions at the interface of visualization research on the one hand side and the geosciences on the other hand side. So before we start, I would actually like to say a big thank you to our presenters and authors, and also to our reviewers for being so productive, even though we are having this current situation. And of course, a big bucket of gratitude also goes to the organizers of EGEV 2020, who did an amazing job of taking the entire conference online. And last but not least, to everyone tuning in into EnvirVis, be it right now, live, or even later. It's great that you're here, and thanks a lot for your interest. So what's going on in this year's workshop? We will have two sessions this afternoon, whereas the first one is a paper session with 3 presentations, and the second one contains our keynote, which is given by Rod Lynn from the Los Alamos National Laboratory, and who will talk about the opportunities and challenges when modeling fire and the atmosphere. And in the current paper session, we will see how visualization can be applied to analyze crowdsourced weather events in the first talk, to look at multivariate volume data sets describing underground nuclear waste experiments in the second talk, and to help soil scientists to assess element distributions in a soil profile in the third talk. And dear audience, so if you have any questions for the talks and for the presenters, please provide them either in the comment section here on YouTube or in our Discord channel, which is linked in the EuroVis program. And I will collect your questions and forward them to the presenter after the respective talks. Okay, so now I think I've talked enough. So let's get to our first paper by Carlo Navarra, Visual Exploration of Climate-Related Volunteered Geographic Information.
The work presented here today is part of a project concerned with the need of European cities and their citizens to enhance their knowledge on site-specific conditions relating to climate risk and adaptation measures. To address this need, the study describes 2 approaches for visual exploring and analyzing data generated by citizens within a citizen science project called Citizen Sensing. The 2 approaches that will be presented are concerned with, first, a low-level overview of the data in a map display, and second, a more in-depth exploration of the data in search for spatio-temporal patterns. The primary aim of the study has been to assess and discuss the potential of such visual exploration approaches in the context of voluntary geographic information. The Citizen Sensing Project is concerned with the development and evaluation of a participatory risk management system. Urban citizens should be able to use this system both as submitters and as receivers of information. So the citizens using the system should be able to voluntarily report information about site-specific extreme weather condition, for example, events of high or low temperature or heavy rainfall, and also of the impacts of these events, but they should also be able to receive information in form of recommendation for best practice adaptation measures, which are based on information from municipal or public authorities. So, the overall aim of this citizen sensing project is to assess if and how such a system can increase citizens' engagement and citizen contribution to urban resilience. The participatory risk management system developed in the Citizen Sensing Project is composed of a web application that enables citizens to submit and report on weather events and their impacts, as well as seasonal observation, a web portal for displaying a direct overview for the collected reports, an open access weather sensor network for collecting specific weather parameters depending on the availability, such as temperature, air pressure, humidity, and precipitation, and of course a database for saving the collected data. The data attributes that are saved in the database are geographical coordinates, data and time, weather event type, impacts, personal level of comfort, photograph, or comments. The latest two are optional. The Citizen Sensing web application aims to facilitate a high level of interactivity by engaging citizens, both as providers of locally situated data on weather impacts and adaptation measures, as well as receivers of specific information on local condition and recommendation on how to respond. A user can select a weather event to report through the app, along with the climate impact for the event. They can add their personal level of comfort relating to the selected event and also submit a photograph and a comment relating to it. Upon submission of the report, the user gets a list of the best practice recommendations relating to the reported event. As part of the Citizen Sensing project, a number of data collection campaigns were held during 2019 in the project for pilot cities: Norrköping in Sweden, Porto in Portugal, Rotterdam in the Netherlands, and Trondheim in Norway. The data collection was performed through different user groups instead of individual user, in order to preserve privacy. Following this, two different approaches have been employed to facilitate visual exploration of the volunteer data. First, a web portal that enables users to gain a low-level data overview in a map display. And second, a visual analysis tool to facilitate in-depth exploration of the data to search for spatio-temporal patterns. The web portal has been specifically designed for a desktop display and features tailored user interaction to support the filtering and assessment of the data. The report submitted from the user are displayed using symbols on a map depending on the reported events. Different events are displayed by different symbols. Navigating the map will filter the submitted reports by location. Submitted reports can also be filtered by time range and thus by campaign, user ID, weather event type, or by the reported level of comfort. Apart from the map display, filtered reports are listed in a panel to the left-hand side of the map display. The visual analysis tool was designed to explore climate-related voluntary geographic information collected in the Citizen Sensing project. The tool has been implemented using the Apache Superset software. It is an open-source data visualization and exploration platform typically used for business intelligence. Superset provides an intuitive interface for creating interactive visual dashboards combined with an SQL interactive development environment. The platform offers a number of visualization charts based on D3 or DexGL libraries that can be dynamically linked for creating interactive visual dashboards. The proposed visual analysis tool encompasses 3 visual dashboards. Each dashboard is tailored to support specific tasks depending on the different use cases. The 3 dashboards make use of 6 different visualization charts to display various aspects of the data. A map view displaying the position of the reported weather events, where color represents the type of event. A map view with an hexagon heat map overlay based on the temperature values taken from the Netatmo sensor network. The height and the color of the hexagonal prism correspond to the average temperature in each bin. A Sankey diagram is used for displaying the linkages between weather event type, impact type, and personal level of comfort in the collected reports. The size of the bands represents the number of linkages between the reported data. Aggregated minimum, maximum, and average temperature values for a spatio-temporal selection are represented in the line graph. These data are retrieved from the Netatmo sensor network. A parallel coordinates plot is used for displaying climate parameters such as temperature, air pressure, and humidity from the Netatmo sensor network. A word cloud has been employed for displaying frequent terms submitted in the comments for reported weather events. The size of the word is proportional to the number of reports. All views in each dashboard are linked by time and weather events through using a filter box. We have explored the potential of the proposed visual analysis approaches by exploring data collected in one of the campaigns held in the city of Norrköping. The data for this campaign consists of 3,917 reports submitted by 28 participants grouped into 3 teams. The data were submitted through the Citizen Sensing web application during the campaign period from May to September 2019. Using the 3 dashboards of the proposed visual analysis tool, different aspects of the data at hand can be explored. For example, the reported data can be explored in relation to the data measured by the sensor network. The spatial distribution of the reports is seen on the map, and the line graph provides an overview of certain measured values. A user can apply a specified spatial or temporal selection to focus their exploration. Spatial filtering is applied through navigating in the map, while temporal filtering is applied through the filtering control panel. Inspecting, for example, the line graph can reveal peak temperature during the selected campaign period. Based on this information, a user can select to explore closer specific time periods for which the reports and average temperature for sensor measurements are displayed in the map views. In addition to this, the parallel coordinate plot can reveal the correlation between different parameters of the sensor data, which is of particular importance for the investigation of heat stress that is influenced by high air temperature along with high humidity. The second dashboard enables analysis of visual material and text contribution for selected events. This case concerns the demand for an overview of submitted data in order to determine to what extent the reports are linked to a specific weather event type. The Citizen Sensing web portal can give a quick comprehensive assessment and facilitates an overview of the type of images and or comments that are submitted during the extreme events, as well as their location. An additional functionality that enables analysis of the submitted textual contributions is provided by the visual analysis tool in the form of a word cloud. The size of the font shows the frequencies of a term, while the word describes the weather events. Both approaches allow the user to zoom in on an area that has, for instance, a high number of reports for a certain weather event or for a certain impact, in order to obtain a special demarcation of an areas that should be further analyzed. Reviewing the images submitted together with the reports might, for such a selection, be indicative of whether the high number of reports was due to a certain climate event or solely because a large number of users happened to be in the same area. The third dashboard and use case is concerned with the analysis of spatio-temporal patterns of specific impacts and the assessment of the data relationships. Here, specific areas in the city can be identified for the period of an extreme event, such as a heat wave, and then examined in terms of impacts types that were reported for this spatio-temporal selection. The Sankey diagram hides in the analysis of such linkages. It shows the distribution of the linkages between the reported personal level of comfort, ranked from low to high during a selected period, the different weather events, such as high temperature, heavy rainfall, drought, strong wind, and storm, and their related impacts. This type of analysis provides an overview as to whether specific weather events were more frequently linked to certain level of comfort and the type of impacts that were reported for specific event type. In this way, they can provide insight into patterns that could be further assessed by means of qualitative research methods. For example, survey or interviews with selected participants, or comparisons to other time periods, campaigns, or pilot regions. A consideration that should be kept in mind is concerned with bias that arise from the data type used in this work, that is volunteer geographic information. Several challenges relating to this arise in the study. The collection of the volunteer data, for example, has occurred through different campaigns across Europe, resulting in uneven distributions. The data distribution for specific weather events might be influenced by user pre-understanding of the offered categories, which in turn might impact the number, distribution, and type of responses for different user groups. Similarly, the impact that can be selected by user might not correspond to the perceived experience of the user, and hence might lead to an overrepresentation of a broader categories, for example, personal level of comfort, rather than providing more specific description of the impact. Bias can also be observed in the crowdsourced sensor data contributed through the Netatmo weather station, considered in this work, since the placement of the sensor can considerably affect the accuracy of the collected measurements. To conclude, the work presented here has described two approaches for visually exploring and analyzing volunteer climate-related geographic information. Information has been collected by means of a web application and visually explored within two proposed approaches. A web portal enabling users to gain a low-level overview of the collected data, and a visual analysis tool facilitating more in-depth visual data exploration. A future direction of the work is to evaluate the visual analysis tool with stakeholders of the different European cities involved in the citizen sensing project, and further develop both the data collection and the visual exploration approaches based on the collected feedback.
Yeah, thanks a lot for this great talk. We have actually two questions coming in. So both of these questions up to now are from Sergei Ignatenko. And the first question he asked is, where exactly is this data stored?
Hi, and good afternoon, everyone.
Nice question, and mainly the data is stored on our server, in the university server, and we have collected the data through as I said on the presentation, through a mobile app, and everything is anonymized and collected in our servers at LIU. Yes.
I hope this answers the question. Next question he asks is, how do you sort out conflicting data reports?
Conflicting data reports. We don't have any method implemented, but of course it's a good question, and partially what our system does is giving the possibility to the user for a specific time and space to see what reports have been submitted. In the moment that and the user can filter different reports and see automatically outliers, but of course we haven't had any automatic methods to sort out the reports, but this can be a future work.
Thanks a lot. Are there any more questions? Please remember you can use our Discord channel as well as the comment or the chat in YouTube to submit questions, and we also still have some time. Maybe until the next question comes, I also have one, and I have a question about the sensor network that you are employing. So I don't quite get the connection to the user. So does every user have to have one of these sensors, or is this an independent sensor network that is implemented in the city?
We've actually, yes.
Sort of compare the measurements to each other.
There have been several campaigns run throughout the project. So in this specific campaign that we have used as one of the case studies in the paper, the user, they haven't used the sensor network, but we had other campaigns run with the students where the sensors, they were installed in school facilities. So the user could actually go through the app, both the Netatmo sensor network app and our app, and check the data that was collected by the sensor. The sensor data, the Netatmo provides only the sensors readings for the current time. So what we did is caching all the sensor data, so we could provide to the user a time series with all the parameters also.
Okay, so while you were talking, another question was coming in by Alexandra Diel. Have you thought about integrating this approach with an analysis of social media data?
Yes, definitely. That's a really good question, and actually, it's part. We are partly starting this on discovering how to integrate Twitter data, scrapping data from Twitter, and actually analyzing it through either machine learning or other mechanism. So to integrate these feeds of data into our system. But at the moment we haven't used social data, but it's in our plan.
Thanks. Okay, no further questions until now, but I have another question. So you said that the users also submit image data.
Yes.
So I'm thinking about special weather events where you, for example, have hail or something. So are there any plans to analyze the images as well? So for example, for hail sizes, you could imagine it would be really interesting to find out how big the hail actually was that was reported in a certain part.
Yes. This is something that has been in our thoughts. Unfortunately, the focus of the project it didn't give us the opportunity to explore this solution, but it's definitely something that we are willing to explore, since we have collected quite a substantial. It's more than 5,000 images, so we have possibility to train machine learning, neural network systems, so to somehow to identify the climate impacts that the user submit report. And of course this connects to the previous question, where we could actually make some sort of identification of if the report is correct, or it's just a random image.
Okay. There is another question that sort of connects to the social media analysis from Fu. Do you think the word cloud evolution over time, word stream, would be useful for this case? So for
Yes. As for the Twitter, as for social media, and the things is that as the project has run, we had campaigns running for 2-3 months or a couple of weeks. So, and only the users involved in the campaign were actually having access to the data due to privacy issues that could have been that somebody would post something that would be controversial. So, not the streaming of this data is a bit tricky, in the sense that we could encounter problem in how do you say, in the what is actually submitted. So, but of course it is an opportunity. There is an opportunity in exploring this.
Okay, last question coming in by Carsten Rink over Discord. You have mentioned the stakeholders. What's in it for the cities where the pilot studies took place?
Sorry, could you repeat?
Yes. You have mentioned the stakeholders of the cities.
Mm-hmm.
So what's in it for the cities where the pilot studies took place? So what's the benefit for the cities?
For the city itself for the citizens, the added value of this project is to give opportunity to the users to understand what are the possible weather impacts that related to climate change, and at the end of each reports, we give them guidelines, suggestion and guidelines on how they can react to certain climate impacts. And of course, the main goal is to create awareness both between the cities and for policymakers to what the normal citizens is experiencing during heat waves or heavy rainfalls or other climate impacts.
Thank you. Okay, so now we're moving on to our next paper. Thanks so much, Carlo, again, also for the competent answers to the questions that were raised by the audience. And now we move on to Felix Wright and co-authors with a presentation about the visual analysis of a full-scale emplacement experiment in the underground rock laboratory, TERRI, using fiber surfaces.
Hi and welcome to the presentation of the visual analysis of a full-scale emplacement experiment in the underground rock laboratory TERRI using fiber surfaces. My name is Felix Wright, and I will tell you something about our motivation, the idea and the algorithm in the first part of this talk. Following this, I will show you several novel ways to use the extended fiber surface extraction for the visual analysis, as well as a demonstration of the usage of this. The expansion of renewable energies is currently one of the essential goals in time of climate change, which in this context, however, not only expansion must be taken care of, but also the elimination of current energy production. Among other things, radioactive waste must be kept away from the environment for a long time, because this has harmful effects on the environment. One possible safe solution is a storage in a geological subsurface. The fitness for such storage depends on the prevailing geological material. But which geological material are suitable for this purpose? In the underground rock laboratory, MONT, research has been conducted for over 20 years on exactly this problem. The rock laboratory is located in Switzerland, more precisely in the canton of Jura, near of the city Saint-Ursanne, in a depth of more than 250 meters. On this region is a predominant geological material, opalinious clay. In detail, research was being conducted into the storage of radioactive waste in the opalinious clay. This is suitable for the storage of radioactive waste due to its variable physical properties, to this permeability to water. The water transport of radionuclides into the biosphere can be practically excluded, and this is therefore an alternative to disposal in crystalline or salt rock. The laboratory is used for research purposes only, and no radioactive waste is actually stored there. Nor will the tunnel system be used for this purpose at any point in the future. Until today, more than 140 experiments have been carried out in the rock laboratory to characterize the opalinious clay. Demonstration experiments allow experiments on a 1-to-1 scale over a long period of time, ranging from years to decades. Numerical simulations support many experiments for planning, purpose, and for process understanding. One of such experiments is a full-scale emplacement experiment. This so-called FE experiment aims to model the construction, waste emplacement, backfilling, and early-stage evolution of spent fuel or high-level waste repository tunnel. Instead of the radioactive material, heaters on bases are used which reach a peak temperature of 100 to 195 degrees Celsius. These are used in a tunnel with a length of 10 meters and a diameter of 2.3 meters. To simulate such an experiment, a coupled thermohydro-mechanical model is used. In such a model, it is usually to calculate 20 or more parameters, like changes in temperature, pressure, saturation, displacement, stress, and strain. Researchers in the environmental science are used to visualizing data using time series displays or displaying scalar data on a plane with predefined color lookup tables as shown here. However, in complex models with many interdependent variables, it is necessary to provide meaningful visual exploration of complex multivariate data. Fiber surfaces are a suitable method for this purpose, since they offer the possibility to work with multi-rate level sets. For fiber surfaces are the generalization of the isosurfaces by Carr. On the left and the middle figure, you can see for each value in the codomain a surface is drawn in the physical domain. The codomain is displayed in the small blue two-dimensional window, and the physical domain is displayed in the three-dimensional window. If you use a two-dimensional codomain, two isosurfaces, one for each component, are drawn. In this right figure, the intersection of both is a so-called fiber according to Carr. So, a fiber is a pre-image of a two-dimensional iso value. By assuming linear interpolation within the tetrahedra, the representation of the codomain in the physical domain can be assumed to be steady. That means a line in the codomain corresponds to an infinity number of fibers in the physical domain, which are then summarized to a continuous surface. That means the pre-image of a line in the codomain is a fiber surface in the physical domain. In this work, we use the fiber surface algorithm of right at all. This algorithm assumes that the object is given in physical domain as tetrahedra. Here, you can see a bending beam, for example, in which at each point a second-order tensor is given. Since we have given a tensor at every point in the grid, we also have three invariants at every grid point, like the three eigenvalues. By using the three invariants as three coordinates, we can create an invariant space. For this bending beam, we get the following invariant space. Here you can see that only the vertices of the tetrahedron are transferred. The relation between the points are not lost. In this invariant space, the engineer has the possibility to look at three relevant quantities at the same time and to analyze them. However, it is important for the researcher to know where these data are located in the original grid. Therefore, a transformation into the physical domain is necessary. Since for each vertex of a tetrahedron in the invariant space exists one corresponding point in the physical domain. This is assessment is simple. For all other points inside the tetrahedron, we assumed linear interpolation. Such all points can be transferred. To identify the areas of interest and region of interest is used in this example as cube, which must be convex or closed. Here you can see this is a red cube and this is our interactor, so-called. The region of interest consists of a triangle surface. So the fiber surface is the intersection between the tetrahedron and the triangle surface. But this algorithm has problems with the calculation of the fiber surfaces, like the numerical errors during the computation of the intersection points. this may lead to slightly different coordinates for the same point when computing it multiple times. Another case are the coplanar tetrahedra. In this case, there is no bijection between invariant space and physical domain. Therefore, we have developed the improved fiber surface extraction. To solve the problems mentioned above, we first of all develop a new extraction algorithm. This is based on a classical clipping algorithm in which we cut off the tetrahedron surfaces from the triangle of the region of interest. In this example, the plane E is the region of interest, the triangles, and ABCD is a tetrahedron. Additionally, we reduce the double calculation of vertices to reduce the numerical errors. A side effect is that our interactor no longer needs to be convex and closed. This was necessary because the calculation of the fiber surfaces reaches its limited in the FE experiment. In this figure, the algorithm without the clipping is used to calculate the fiber surface. Here, you can see very well the weaknesses of the old algorithm, because in this data set many planar tetrahedra occur. With the new algorithm, these errors no longer occur. The following picture shows the fiber surface extraction from the tunnel with the clipping algorithm, as shown in the upper right figure. A significant improvement can be seen here. On this figure, you can see the inside of a tunnel with the pressure is shown on the fiber surface. This also makes it easy to identify the heaters that were installed in the tunnel for the experiment. Now we come to the visual analysis. With the new algorithm, it is now possible to analyze the FE experiment. For this purpose, some possibilities are shown which result from the improved fiber surface. First, we show the extract fiber surface. This is a standard way to use fiber surfaces for analysis. Here, a region of interest or interactor is marked in the left attribute space, consisting of the three eigenvalues and displays in the physical domain. The region of interest or interactor is highlighted as a wet cube. So the three heaters and the tunnel are clearly visible. Additionally, a sloping surface is visible which could not be recognized before. This way is especially useful if there is already an understanding of the corresponding attribute space. If an overview of the dataset is to be gained first, it is advisable to use the second possibility. This possibility is the sliding fiber surface. In this method, the interactor is placed in a region of interest and the interactor is controlled by a sliding algorithm. In this example, the attribute space, consisting of temperature, the duration, and the vertical stress, is investigated. In this example, A video is shown in which the interactor penetrates the corresponding attribute space and displays the fiber surface. This example shows the interesting area around the heater. With this, the effect of the temperature on this area can be examined very well. A last possibility is a connected fiber surface. In this case, several extract fiber surfaces are connected. The possibility is used that the algorithm also works vice versa. So, first, an interesting area in the attribute space consisting of the 3 eigenvalues is used. So, interactor is here this red line. The rest from the interactor is outside the window. So this is mapped into the physical domain on the right side, in which the tunnel extends and the 3 heaters are assessed. Here we select the middle heater and use this created area as an interactor and map this another attribute space. So he is highlighted in blue in this window. So this attribute space consists of temperature, saturation, and critical stress. This result is a complex interactor surface, which can now be used as a new interactor since the improved algorithm is many times faster and more accurate than the old one. This is mapped back into the physical domain and shows us now, in addition to the middle heater, all areas where similar values were found. This is due to the fact that the different tetrahedra penetrate each other in the attribute space. So, summarized, we presented an improved fiber surface extraction algorithm. We can use complex interactors to the speed up of the algorithm, and we reduction of errors throughout our linear interpolation, and we present several novel ways to visualize data. Based on these, in the future we will extend and analyze in collaboration with domain scientists. We will the fiber surface applied to other experiments from the underground rock laboratory, and we will improve the attribute space visualization. Thanks for your attention.
Yeah, thank you very much for this talk, Felix. All right. So up to now, I haven't seen any questions, neither on YouTube and also not on Discord. So don't be shy. Just go ahead and type in something. And in the meantime, I'm going to ask a question. So you said that you improved the fiber surfaces algorithm, and I would be interested in the general performance. So is it possible to do all of this in real time, or is there any need to pre-compute everything?
Yes, for the default example, so for a dataset with 1 million triangles, tetrahedra, and an interactor with 2000 triangles, it is 1 second, so it's no problem. Mm-hmm. This is only for the connected fiber surface. There is a problem when we have over 1 million triangle and connectedness with over 1 million tetrahedra. So this is a problem in this point. Okay.
So you would basically recommend someone who would apply this, you would say, okay, please decide beforehand for the 3 variables that you would like to see or where you would like to explore the interconnections. And then you would pre-compute it, and then you would give it to the researcher and say, okay, now you can go ahead and explore.
Yeah, sure.
Yeah. So what would be the 3 most important variables in such a simulation of a full-scale experiment? And what would you want to see?
For this example, we use this variables from the experts, from the domain experts. They say, okay, for us it's interesting the saturation. You can see in the saturation why the water is in this location or not. Mm-hmm. And when we have the heater on this position, the saturation is very high. So, mm-hmm. And the problem is if in the clay stone the saturation too high, the clay cannot hold the water more, and so the
it just flows through.
Yeah. And the other variables are the temperature, also important for this point, and the stress is interesting. Whereas elements, when you say so, when you have earthshake, also the elements,
You mean that the strata or the geological layers that they stay?
Yes.
Okay. So if the pressure, like if the temperature gets too high and if the pressure gets too high, then these strata can be disrupted.
Yeah.
Okay. Yeah. Okay. Very interesting. Okay. We still don't have any questions. I'm also out of questions. It was a very interesting talk. So maybe we just move on to the next talk. And if there are any more questions for this talk, then there is still the opportunity to put this into the chat. And they might be answered later then. All right, so next up is Fang Pham with Soil Scanner 3D visualization for soil profiling using portable X-ray.
Soil Scanner 3D visualization for soil profiling using portable X-ray fluorescence by Fang Pham, David Weindorf, and Tommy Duck from Computer Science Department and Plant and Soil Science Department, Texas Tech University. Current approach to soil horizon analysis using pXRF spectrometer. pXRF stands for portable and handheld X-ray fluorescence. It is non-destructive and cost-effective method to quantify elemental concentration from soil pattern. Soil scientists can just go to the field, excavate a pattern, or use a core to extract soils that need to profile. Use the pXRF device to scan the soil surface for elemental concentrations. After that, the elemental concentration is exported into CSV files and ready to be analyzed. With the speed of current pXRF technologies, it is possible to take about 500 to 600 data points per day. After having the data, currently, scientists use different software to analyze the data from Microsoft Excel to tools such as ArcGIS or Saga or Global Mappers, and even sometimes they need to create custom codes using MATLAB or Python as well. While collecting data is fast, analyzing the data is still time-consuming and it's a burden for the soil scientists. Furthermore, most of the graphics generated are merely for reporting the result to the public without having the interaction to support further analysis. We propose a data visualization approach for on-the-field soil profiling using pXRF device, in which soil scientists and data visualizer work closely to provide a solution for on-the-field soil profiling using pXRF device. The stages include data collection, data processing, data visualization, and interaction to support analysis and exploration as well. For further details. Data collection and data cleaning. In data collection, soil scientists going to go to the field, make a pattern, and they're going to use portable X-ray devices to scan every of the cells that they made in the profile. A pattern is a soil surface excavated by soil scientists, and there are 13 horizons from top down, naming from A to M. And also, there are 10 vertical slices from left to right. Each cell is of size 10 cm by centimeters, and the total of 130 cells. They use the pXRF device to scan every individual cell. It is relatively fast to complete a scan. It's about 30 to 60 seconds depending on the soil scientist. Element concentrations are exported to CSV file and ready to clean up and analyze. Data processing. First stage is to do the data cleaning. First, we'll remove the LOD or limit of detection values, which are the elements that couldn't be detected by the pXRF device. We'll detect and give warnings about the outlying data if there is. Furthermore, the portable X-ray fluorescent technology allows the soil scientists to do on-the-field analysis by generating several of the pedological features from the detected element. For instance, we will automatically compute and add the Roxton weathering index, and we'll also calculate an elemental ratio of elements resistant to weathering, or SI, or stable index for short, or the silication index, or DI. On the right, you can see the distributions of these indexes and elemental ratios that computed and added to support the pedological analysis. Furthermore, while the scanning points, as discussed above, are discrete, the elemental distributions are supposed to be continuous. Therefore, we use crunching algorithm in order to do the interpolation and display the data in continuous manner. Visualizations and interactions. In our previous work called ENVIRVIS, we provided 2D graphical analysis functionalities such as the correlation graph for all the detected elements, the correlation pair, the correlation between a pair of elements, pairwise elemental spatial distributions, the elemental distribution over different horizons of the soil profile, and also a way to compare different soil profiling approaches. In this book, we are proposing a program called Soil Scanner. It is a 3D approach to soil profiling, and this approach is inspired by the medical scanning process, such as brain imaging and CT ultrasound scanning, which allow doctors to continuously navigate different cuts of the brain or body. Similarly, in soil profile analysis, the soil scientists state that it is essential for them to navigate through vertical or horizontal slices of a soil profile and visually observe how the element distribution slowly change over depth or horizontal spaces. This is the main view of soil scanner with the menu, the overview view, the vertical and horizontal distribution view, and the pairwise comparison view in detail. Elemental distribution overview. This provides an overview of 3D elemental distributions over the spatial space of the profile. It orders the elements to groups chemicals with similar concentration distribution together. So if they're similar, they can stay together. Besides color, the third dimension in 3D visualizations in this one help to quantify the distribution differences. We also provide a digital photo for better correlations of the distribution on the soil profile. The vertical and horizontal distributions view. This will provide the elemental concentrations across the top-down horizon at the horizontal cut. At the same time, it also provides the elemental concentration across left to right at the vertical cut. In this case, soil scientists tend to use line chart for representing the distributions vertically or horizontally. However, line charts has the cluttering issues when we have large number of elements to display. One of the ways that they tackle this is to use stepwise line chart, which means that they're gonna create different bases for different elements by using line charts. However, if we use line chart, it has the cognitive issues about not being able to recognize the base. Therefore, our proposal for them is we're gonna use ordered stepwise area chart to resolve these issues. The area chart is to make sure that the user is gonna be able to recognize the base of each of the elements. And the ordering options is used to assure that the elements in the back will not be hidden by the elements in the front, because the elements with lower values in the front will be displayed first. Furthermore, we also provide the handles so the users can drag this and scale the chart size if they want to. Correlation details view. Soil scientists often like to view and compare pairwise elements, so they can select any of the two elements to compare in details. In this details view, users can use full orbit controls as zooming, panning, rotating to further investigate the distributions and compare them. Interaction. The interactions are best explained via a quick demo videos. Users can select a soil profile to analyze from this control menu. By default, all the detected elements and the computed pedological features are displayed in this menu. They are also grouped by packages such as heavy metal, plant essences, pedology, and others. These packages are of interest and specified by the soil scientists. The 3D spatial distributions of the elemental concentrations are shown here. You can use this handler to expand or compress the space between elements while analyzing. Full orbit controls such as zooming, panning, and rotating are provided to explore the distributions. Users can also use the ordering options given here to group similar elements together, and the ordering options include ordering by the distribution values at the cut point of the vertical planes and horizontal planes, or by the average values over the horizontal plane, or by the average values over the vertical planes. And when you change the plane cut point, the order won't change. Or let's say if you change by horizontal average, the order won't change when you change the horizontal cut point, but it will not change if you change the vertical cut point. Users can select individual elements to analyze, or they can select the whole package at a time. For instance, if we would like to analyze the plant essential elements, we can just simply deselect the other packages. On the right side, it shows vertical elemental distribution at the vertical cut plane and the horizontal distributions at the horizontal cut planes correspondingly. When you move the cut planes, the graph will change to reflect the distributions accordingly. Furthermore, we also provide this handler to resize the chart if needed. Furthermore, soil scientists often like to compare correlations of distributions from pair of elements. User can select the elements and they won't be loaded into lower views for analysis. Full orbit controls are also provided in this view for further investigations. In case the user would like to reset the views, they have the option to do so either by the main view, details view, or all the views. Evaluations. We receive positive feedback from the soil scientists, and also recently National Resource Conservation Service honors our approach in one of their articles called Elemental Analysis Using Portable X-ray Fluorescence Spectrometry. Furthermore, we are currently having an NSF I-Core grant in order to interview and find out further requirements from soil scientists to build software to help them analyze the data coming out from portable X-ray devices. Conclusions. In this project, data visualizers work closely with soil scientists to develop a soil profiling software called Soil Scanner. While the soil scientists help to understand the data and provide requirements, the data visualizers assist in giving appropriate visualization for the requirements. We're also emphasizing on interactions to support further analysis rather than just merely reporting the result to the public. Furthermore, in the future, a tangential adaptation of this approach can be used to analyze the cores extracted in a larger geographical areas. We will use machine learning to recommend graphs to individual users based on their context. Furthermore, we'll also use machine learning to provide in-field information about soil features. This one will be helpful for the soil scientists to speed up their job while they're still on field. Thank you. And if you have any question, you can address now, or please contact vitpap@ttU.edu or tommy@attitude.edu. Thank you for watching.
Great talk. Thank you very much. And I already got a question here from Carsten Rink. The visualization and interaction options are very impressive. However, I would imagine this is a very different way to analyze data compared to what soil scientists are used to. How do the domain experts like your application? How do you have any user studies? How well they can work with this framework?
Yes, we actually work closely with two soil scientists in our university on this project, and we receive positive feedback from them. And also, because of that, they encourage us to go further and propose our method to NRCS, as you see. And we receive also the positive feedback from NRCS. And NRCS means National Reservation, Soil Reservation Services. Yes.
Thank you very much. Further questions, please. I see someone's typing. Okay. Carsten says, thank you for the answer.
You're welcome. Yes.
Okay. While we were waiting, I also have a question. So you looked at the variable concentration distributions, basically, or the element concentration distributions throughout the soil. And I wonder if that's the only variable that soil scientists are used to. Is there anything else that they usually record, like temperature or water content, or I don't know. So,
I see. I understand. So actually, soil scientists will have many different kinds of variables or features that they would like to have, but in this technology we work closely with the soil scientists who use the portable X-ray fluorescence only, and this portable X-ray fluorescence they produce could detect about from soil could detect about 20 to 23 elemental concentrations, but from those elemental concentration they can extract further information from there. Like I already gave 3 of the indexes about pedological properties that they want to, and many of them are preferring to work to extract further information from the elemental individual elemental concentration, but mostly based on machine learning to predict those other features. Yes, they do have like moisture or pH also. Yes, but mostly again using machine learning, not directly coming from the portable X-ray devices itself.
yeah, thank you very much. Yeah, so these pedological feature indices that you were talking about, I didn't actually see them in the interactive tool. So are they just usually displayed along with the individual elements, or are they integrated?
Actually, they already calculated and be visualized there as one single element.
Okay.
Yeah, it's there. Actually, there is a package for those. Yes, I didn't select that, but I can select the package for pedology, and those will display the 3 indexes that we calculated and put over there.
And each of these index, well, I guess there are different sets of elements that contribute to these indices.
Right. They are computed by the elements that on top of because where we have the menu, on the top menu will be the individual elements, and at the lower menu will be those generated by actually there are formulas there from the soil scientists. Let's say for one of them will be computed based on the Fe content plus oxygen there.
Yeah. And I would figure that for the soil scientists, I mean, you can always look at some sort of summarizing index, but I would imagine that they also want to see the individual elements that are basically contributing to this summarizing index.
I understand. Yes. Actually, that could actually we can create one more layer of the packages over there. At the lowest layer will be the package, then above will be the computed one, and on top of that we can put individual elements. That one is the thing that we were thinking of as well. Thank you.
Yeah,
Yes.
that makes a lot of sense.
Right.
Okay, so I'm still waiting for questions. Again, don't be shy. Just put some questions, just type them in. You can also still ask questions for the other talks. We have some time to go. Right now, it doesn't seem that anything is happening.
While waiting for question, I have a request actually. I'm running an NSF core project related to this soil analysis. So anyone who is working with analyzing soil data, then may I have your contact and can I arrange a quick interview with you too? Thank you. Because this one is a requirement for our project.
All right, yeah, so you heard him. If you want to provide your contacts, you can do that. Of course, you can stay in contact with him over our Discord channel or just write him an email. So he provided
Right, thank you.
at the end of these slides. And I see someone's typing a question, so we'll just wait a little bit, waiting with excitement what this question or a hint or comment might be. Okay, Michael Böttinger asks, nice talk. It would be interesting to get an example of what the domain scientists learned by using the visualization.
Oh, actually, they learned that one of the interesting thing is that we use the 3D visualization so they can quickly see one of the outlining points in their data. So actually when they do the scanning of the soil profile there and they made a mistake that very thin after the behind the soil there is a big rock inside it. So there is one point in that one it's show very high values of calcium, and with this visualization they say okay, there is an issue with this scan, so we should remove it. And they also say that this one will be a lot better if it could be done in real time. So when they are still on the field and they see these issues, and they can just remove the soil, the rock, or scan next to the place instead of scanning right to the rock there and make an error in that place.
So I understand you correctly, the soil scientists can immediately port their data into this tool while they are still on the field, and they can say, hey, this looks valid, or this doesn't look valid at all.
Yes. Or they say maybe if they can have this in field, then it will help them to navigate in different locations while exploring the profile.
Yeah, okay, I see. And are there different devices to do that? Do they all have the same data format, or would there be significant differences if you use that brand of a device or the brand of a device?
Yes. Actually, there are many different producers like ShyUp, Hitachi, Olympus, and Brookers, Thermo Fishers as well. But mainly by now we are working with Olympus devices. But of course, in the future, in order to expand this product for multiple users, we will have the tool to extract the data from different devices and put into the same format for our how to say application. This one is what we are actually contacting and working with the manufacturers themselves as well.
Oh wow, yeah, that's pretty cool. And I figure that would also be interesting to see what the differences are in the measurements.
Yes.
Okay, great. Thank you very much.
Yes, thank you.
Okay, so I would say the invitation is still there. So if you have any more questions to all of our authors and our presenters, just go ahead and post them in our Discord channel. And I guess they will stick around and look at this channel and see your questions and maybe answer them even. And I would say this concludes our session, our first session. So please make sure to tune in later again. When Rodlin is speaking, this session will start in, wait, I even have to check this. It's going to start in half an hour or in 45 minutes actually at 3:30. So tune in and I'll see you